Today's topic we will be discussing in this video is chemical equilibrium and Le Châtelier's principle. Okay, so let's start out by explaining what is chemical equilibrium. Well, when we talk about equilibrium in chemistry, we're not necessarily saying that everything has stopped. Rather, we're talking about a dynamic balance. It's in a dynamic equilibrium. So I'm going to ask you guys to picture this. So a reaction is going forward and backward at the same rate. The concentrations of the reactants and products are going to stay constant. So let's say we have N2O4 is in equilibrium with 2NO2. Now, since we could see that this reaction is at equilibrium, the concentrations of N2O4 and 2NO2 are going to stay constant here. So, let's say we put some N2O4 in a container. So we increase its concentration. Over time, so as time progresses, some NO2 is going to start forming, and eventually that'll level off. Now, a big part about equilibrium that you'll be tested on a lot is graphs in that aspect of it. So let's say we have some initial amount of N2O4. You'll see that N2O4 amount is going to start up, but it'll decrease over time. Now, we have 2 NO2, so it's going to form 2 moles of NO2 for every 1 mole of N2O4. So its concentration, which is initially 0, is going to increase faster, but again, we'll see it'll level off. Now, where do they level off exactly? So let's say that's time 1, that's time 2, and that's time 3. If we draw some dotted lines at each of these points, we'll see at time 3, that is when we see our reaction reach equilibrium, right? So, if the concentrations of both gases stop changing, as we see here, does that mean they're equal? No. It just means that they're stable, not necessarily the same. All right. So we can compare these not equal concentrations using our equilibrium expression, or in chemistry, it's called K. Now, this is how we are going to compare the concentration of products to reactants at equilibrium. So our general formula is, I'll just use this K here. K equals, and we'll put KC. The C stands for concentration. This is KC equals the concentration of our products to the power of their coefficient over the concentration of reactants to their coefficient. Now, let's say I gave an example reaction, Haber's process. N2 plus 3H2. We can put state symbols here. Is in equilibrium with 2 ammonias. If we were to put this in an equilibrium expression of K, that would be, what do you guys think? I'll give you a second. It would be NH3 squared over N2 times H2 cubed. Notice how our coefficients became our exponents here. All right. Now, something else with this is that solids and pure liquids are ignored in our equilibrium expression. So if we had, let's say, NaCl solid is in some equilibrium with Na plus aqueous plus Cl minus aqueous, only Na plus and Cl minus would be in this expression, and there would be no NaCl in the denominator, right? Now, if we know that Kc's value is some really large number, like let's say it's 10 to the 5th, what do you guys think that'll tell you about this reaction at equilibrium? That'll tell us that it favors the products, right? Because in order to get a super large K value, wouldn't the numerator have to be some super large value comparatively to the denominator? So that means that the products are going to be favored at equilibrium. Now, if it was something like 10 to the negative 5th, then obviously that would mean our reactants are favored at equilibrium. So just keep that in mind. Next, let's look at Le Châtelier's principle. So, Le Châtelier's principle is going to tell us how a system at equilibrium responds to stress. So basically, the reaction is kind of trying to undo this change. It's kind of like cause and effect, or like reaction response kind of thing. And we have I like to say like a big three system changers or stresses for Le Châtelier's principle. We have one would be concentration. 2, I would say, is temperature. And 3 would be pressure / volume. All right. So let's use the Haber process again. NH3. Now, it's given that the Haber process is an exothermic reaction. Its delta H value is less than 0. Which means, let's imagine heat as kind of a product. Of this reaction, right? So, when I do something relating to one of these three stressors, the equation or our reaction is going to try to do the opposite effect. So let's say I add concentration of N2. Then the system is going to shift towards the products to use it up, right? It's going to consume some N2 to reestablish equilibrium and get that K value back to normal. When the system isn't at equilibrium, then we use this Q value instead, right? So if Q is less than K, like in this case, that means if we remember our K expression as products over reactants, then we want to make our numerator bigger, right? For Q, not for K. We want to make our numerator bigger to get it to equal K. Well, to do that, we'd have to shift to the right? And then, so we know that this is an exothermic process. So heat is kind of like a product in this. So if we add more heat, let's say we do this in like a warmer environment, then the reaction is going to shift to the left to counteract that. Oops. All right. Now this last one, pressure. Now, I did pressure / volume because, as we know, a decrease in volume is going to increase pressure, right? So if I were to decrease volume in this sense, it would, so volume decreases, pressure increases. If I were to decrease volume, yielding an increase in pressure, what do you think the system would do? Well, it would shift to the side with fewer moles of gas. Imagine it like this. If we have like this point of view, so we have some N2 molecules, then we have 3 H2 molecules versus a side of products with just two NH3 molecules. Obviously, this side is going to have more pressure than this side, right? So if we increase pressure, according to Le Châtelier's principle, in order to counteract that, we're going to want to shift to the side with less moles of the gas or less pressure to drop pressure back down. All right. So now let's do some practice stuff with this. So what would my system do if I were to add more NH3? Yes, if you said this, then it would shift towards the reactants in order to drop our Q value to make it equal to K. What if I were to place it into a colder environment and thus lower heat? And if you said shift it right, then that is also correct. And what if I were to increase volume and thus decrease pressure? What would it do in this case? And yes, in this case, it would go the opposite direction to the side with more moles of gas in order to increase pressure, right? All right. So let's wrap this up with a little quiz. Let's say I have the reaction A plus B is in equilibrium with C plus D. First write me my K expression. We're assuming all of these are gases, let's say. Gases. So first write me my K expression. Then what will happen after I remove D, and then let's say this is an endothermic reaction. What will happen if I were to increase heat? All right, well, that's all there is to it. And just the basics of chemical equilibrium. And I hope you guys enjoyed.